Just a little bit about Mark Pernicone. I've known Mark for a number of years. He originally was from the Chicagoland area, and he got his bachelor's degree in civil engineering in 1974, and stayed on and got a master's in 1976. After graduating from Purdue, he left and took a job with the Lyles company, and worked there for a number of years until he decided to come back to Purdue again and pursue an MBA, which he got from the Cranmer School in 1984. And so Mark has got 3 Purdue degrees. That's pretty impressive. And after leaving Purdue the second time, he took a position with the Charles Pankow Builders, and also over the years worked for C.E. John Company and Westfield Corporation. And so he's been involved in numerous construction activities over the years. In 2012, he became executive director of the Charles Pankow Foundation. And just a little bit about the Pankow Foundation. It was established to provide the AEC industry with better ways to design and build. It was established in 2002 by Charles Pankow, founder of Charles Pankow Builders, leading U.S. design build contractor. And the foundation's continues to advance his legacy of innovation. And so that's really what it's all about, sponsoring research and developing new and innovative ways to build. And Mark may say a little bit more about that. But I wanted to recognize them because they have been involved in helping to put this on. Mark is a recent 2016 CE AAA awardee winner. Is recognized for that, and he's currently the chair of the CE Advisory Council. So I'd like to call Mark to come on up, and please introduce our speaker.
Good afternoon. I'd like to welcome students, alumni, faculty, a few members of the CE Advisory Council. Glad you could be here. Again, my name is Mark Pernicone. I'm Executive Director of the Charles Pankow Foundation, and I'm kind of playing a dual role here. I'm also the incoming chair of the CE Advisory Council. We're really happy to be able to co-host this with the Lyles School of Civil Engineering. Research is important to us, and there is a lot of great research going on in civil engineering, and a lot of it's being done right here at Purdue in all the disciplines of civil engineering. Bowen Lab in particular is probably the premier structural lab in the country, and I hope you can join us after Ron's presentation to see a couple of projects we're sponsoring that are actually undergoing testing right now at Bowen. I want to again thank a couple people, the Lyles School, in particular Rao Govindaraju, or GS as he likes to be called, Mark Bowman and Sue Khalifa for helping us put this together. My job here is to introduce Ron Klemencic, and one of the most exciting things in my professional career has been able to work with Ron over the last 5 years. Ron's day job is chairman and CEO of Magnusson Klemencic Associates, or MKA. And just to be clear, I don't work for MKA, and that would give Ron a heart attack thinking about that for a minute. And if I was to kind of talk about all the awards Ron has gotten just in my 5 years, there wouldn't be any time for Ron to talk. But just to localize it here to Purdue, Ron was a BSCE Purdue in 1985, went on to Berkeley for a master's degree. He was a recipient of the CE Alumni Association Alumni Achievement Awards, and one of the rare recipients of the Distinguished Engineering Alumni. And just for fun tomorrow, while he's on campus, he's being inducted into the Co-op Hall of Fame here at Purdue. When I describe Ron, I kind of use 3 words that aren't always used together. Visionary structural engineer. Sometimes you see those words separately, but not always together. And Ron is truly unique in his industry. To the point where I would say if structural engineering had a Steve Jobs, it could very well be Ron Klemencic. So with that, I'll introduce Ron Klemencic. Thank you.
Mark asked me when we were putting this presentation together to try and connect research and meaningful research in the laboratory to building and designing construction practice, stuff I do every day, practicing structural engineering, designing buildings, building buildings, and how does research help advance that and improve that? And that's the mission of the Charles Pankow Foundation, which I am honored to be on the board of directors of. So that was the charge, talk about how research informs current practice. My can do that. What I do in my day job is design tall buildings, and probably most notably in high seismic zones. That's maybe what I'm most well known for doing. And I can talk about that. But to me, that's stuff that I always talk about. And for Purdue, I wanted to try and set the bar a bit higher. Or perhaps dig the hole a bit deeper. I'm not sure. You'll be the judge. But I remembered back to when I was a senior at Purdue, and in our senior class, there was a dinner that I attended late in the year. And at that dinner, there was a speaker. I don't remember his name. Excuse me. I don't remember exactly what his affiliation was, but I remember his message. And his message actually has stuck with me all these years, for 32 years since I graduated. And I guess my goal, because I like to set the bar high, is 32 years from now, one of you students will come back here and say, I went to this presentation when I was a senior. I don't remember the guy's name. I don't remember his affiliation, but his message has stayed with me all these years. So, the bar is very high, and so if you'll permit me, we're going to jump into this. The secret to everything. Oh, yeah. This is maybe a Steve Jobs moment. What do I mean by this? I reflected on my career and how I got to where I am. I've enjoyed wild successes. Incredible. I can't even believe where I am in my career now and all the wonderful things I've done, people I've worked with, projects I've worked on. But what is the secret to all of that? How did I get there? And that's really what I want to share with you. Not the Ron Klemencic story, but the underpinning of the philosophy of what drives that outcome. So, with that, I'm going to launch into my hypothesis for the day. And I think the secret to everything lies in two fundamental questions. And if you can answer those two questions, therein lies the secret to everything. So the question that I'll pose to you first starts like this. The sky is blue. The grass is green. The speed limit's 55. Things that we see, take for granted every day, we accept in our lives, we process them and move on. Why? This is question number one. Why is the grass green? Maybe you care, maybe you don't. Why is the sky blue? Maybe you care, maybe you don't. Why is the speed limit 55? Why gives you, if you understand the why, right, it gives you the underpinning and the power and the platform from which to build. And so if you can understand the why of why something is the way it is, you stand a chance of changing it, or at least building from it somehow. Now, you're not going to change the color of the sky or the color of the grass, but these are everyday examples. Ultimately, I'm going to relate this back to structural engineering so that you can see some classic examples in my career of how this applies. Let's go back to our speed limit conversation. Speed limit's 55, or is it 60? Or is it 65? Or is it 70? Or in the Autobahn in Germany, right, there is no speed limit. Why? Why are these numbers those numbers in particular? Who set them, and why did they exist in the first place? It's a simple everyday example, but that premise, if you apply it throughout your life, not just in engineering, but throughout everything in your life, and try to understand the whyness, it gives you basis to move on. So, let's get into some engineering examples and explore this notion of why. So I'll offer this, that in the beginning, there was darkness. And God said, let there be light. And there was. And then at some point along the way, God inspired us to write something called the building code. Now the building code is littered with all kinds of regulations and rules and formulas and facts and limitations and like, for good reason, right? We're trying to create safe, inhabitable places to be. But when you start to peel back the layers of the building code and try to understand why are these things there? Where did they come from? What is their purpose and why are they there? It's very revealing. And in my career, there's been a couple of classic examples, which I'll share with you today, that aren't written in stone. They weren't passed down from the mountain by Moses. R. First letter of my name, R. Ron. There's a factor, there's a number in the building code, a parameter called R. Well, what is R? R comes from seismic engineering. And in seismic engineering, we have this R factor embedded in the building code. It's a response modification factor. Wow, big, long term. What the heck is it, and why is it there? What is its purpose? Before we talk about R, we have to think about what came before R. And before R, there was something called R sub W. And before R sub W, there was something called K. Where did all this come from? All right, so we got to go back in time. And back in time takes us to the 1940s and 1950s on the west coast of the United States, where our forefathers were starting to build the framework to do seismic engineering of buildings. And so the framework that is embedded and the philosophies embedded in the code today for seismic design started in the 1940s, or really got traction in the 1950s. That's where it started. This starts to help us understand what it is and why it is. What was happening in the 1950s? Of course, we didn't have computers to do calculations. We did calculations by hand. Well, we didn't, but our forefathers did. Hand calculations to describe and understand a very challenging structural response. That is the idea of when an earthquake comes and hits a building and excites a building, the philosophy, the expectation is that the building will respond to that earthquake and concrete will crack, rebar will yield, steel will yield, and in doing so absorb that energy. It will respond non-linearly to that ground shaking. But in the 1940s and 1950s, there was no way to do those calculations in a practical sense. So what was done, and what this complicated engineering graph points out, is that what we're looking at here, right, on the vertical axis is acceleration or ground acceleration. On the horizontal axis is the period of vibration of the structure in question. When we talk about the real earthquake, it's this dashed line. An earthquake that happens, in this case, one time every 500 years. We'll call it a design earthquake. In that earthquake, it's expected that this building is going to yield and crack and deform and respond non-linearly. But there was no ability to calculate that. So, what our forefathers dreamed up was, if we reduce that earthquake to a lower value, something that brings the demands down into the linear elastic range, so that we can actually do a calculation and come up with how much steel, how much concrete, how much rebar to put in the building, we have a chance. And then if we detail those connections and pieces properly and add ductility to them, they'll take up that gap, that nonlinear response gap. And so what's happening here, right, is that this real earthquake, which is up here, is divided by some number ranging from 2 to 8, and it creates this green line here, which is the design, the elastic design forces that an engineer would actually design to. So, why does R exist? Convenience. At the time, it was inconvenient to design inelastic structures with the computing methods at hand. So it's not based in science, it's not based in physics, it's based in philosophy, and it's based in convenience. But today, many engineers look in the building code and they think it came down the mountain from Moses and R equals 8. My God. All right, R equals 8. So what we've done, we've taken our earthquake and we've divided it by 8. 12% of the actual load that may exist when an earthquake comes. And we look at this and say, well, that applies to ductile systems. Things that will respond very ductily, like lumen frames, buckling restraint braces, things that will absorb a lot of energy. And so the code assigns that this magical number 8. Buildings that don't respond so ductily, the building code gives it an R of 5 or sometimes even less. The notion being that these buildings that are less ductile, of absorb less energy, so we'll divide by a lesser amount and reduce that curve to a lower value. The problem with this in the building code is that R equals 8 might look something like this. This is intended to be the floor plan of a building. The little dots, if you will, are columns. And interconnecting the columns are all these beams. So every column and every beam is connected. And if you design them and detail them for a ductile response, you can imagine, wow, this building might actually absorb enough energy so that when we divide the real earthquake by 8, size these pieces for that there's enough pieces in the building and enough activity that it will actually respond philosophically as hoped. The building code, though, would also say this building is R equals 8. I have 4 beams. It's a monoframe, and all you see when you look in the building code is a monoframe, R equals 8. Doesn't matter if it's that one or it's that one. So again, the premise here is, why is it that way, and does it really achieve the outcome that we are looking for? If you put it in the context of a less ductile system like a shear wall, here I put a shear wall all the way around my floor plate. Maybe this is a warehouse building, and it's this punched wall with opening windows in it, per se, or perhaps it's a tilt-up warehouse, but there's walls everywhere. R equals 5 according to the building code. That's also R equals 5. I took all the shear walls out the outside away, put a little core in the middle. Because we call it a shear wall, R is also 5. Does that make any sense? Maybe not. So it goes back to this premise of why are things this way, and why they're this way. Why is R in the code to begin with? It's a matter of convenience. So we can actually do our work. It's fundamentally, it's underpinned with philosophy, but it's not underpinned with science. When we come up with these numbers, R equals 8, R equals 5, no one did any studies when they came up with those numbers. It's not based on engineering or math or physics. It was negotiated in a committee meeting. And so you have to take pause and wonder why these things are there and what are their real use. Second example I'll offer, and this is my favorite. So in this case, again, we're in the seismic world. And in the seismic design world, I don't know if you can read this, but this is a table in ASCE 7 in the building code, special reinforced concrete shear walls. And for special reinforced concrete shear walls, oh, lo and behold, there's an R factor. Ah, lovely. But more interestingly over here, there's a height limit, 160 feet. The building code limits a special reinforced concrete shear wall to 160 feet. Why? Why is there a limit? Why is it this really odd number of 160? It seems like somebody thought hard about that. And so I was curious and I did some digging. Where did this come from and why is it there? Why is it 160, which is really odd? But I learned this, we got to go back to 1920, Los Angeles. And in 1920 Los Angeles, the city council was debating the urbanization of downtown LA. And what they didn't want, and it's well publicized, they didn't want what they call Manhattanization of Los Angeles. They liked the sunshine, they liked the warm weather, so the city council passed a resolution that limited building height in Los Angeles to 150 feet, 150 feet, in 1920. And that limitation stood for 30 years. Okay? In the late 40s, early 50s, structural engineers started to work on seismic design provisions. And they started to think about buildings of importance. What might be a building of importance? Well, at that time, lo and behold, the city of Los Angeles, according to Charles Pinkham, who's a very famous seismic engineer on the West Coast, he said in the 1950s, Los Angeles removed this height limit of 150 feet for 13 stories, and they removed it because the city council was receiving a lot of economic pressure from developers wanting to build taller and bigger buildings. So the city council removed the requirement. But the structural engineers, searching for a threshold, said, wow, LA had this 150 thing going, let's glom onto that. Because what they were trying to do, in fact what they said in the 1959 building code, the structural frame shall be provided for all buildings taller than 13 stories. Where is this all coming from? You'll recall back here, LA for zoning purposes had 13 stories and 150 feet for shadowing purposes. What was being built at the time were a lot of masonry buildings from the 20s to the 50s, masonry bearing wall buildings, and some buildings, as they were getting taller, included a steel frame. And after earthquakes that occurred and earthquake reconnaissance, there was anecdotal evidence that buildings that included this steel frame did better than buildings that didn't have it, than bearing wall buildings. Thus the requirement, anything taller than 13 stories must have one of these frames in it. Not based on science or math per se, based on field observation of earthquake damage. That seems rational at the time, nothing inappropriate. But then we find out this in the 1961 code, and now we're into the Uniform Building Code. So now this has gone national, beyond the city of Los Angeles. Structural frame, buildings more than 13 stories or 160 feet. Well, wait a minute. Where did the 160 come from? I thought it was 150. It's a typo. No lie. I looked back at the committee records, the committee notes from the committee meetings back in 1950, and the intention was to adopt the previous LA City Council limit of 13 stories or 150 feet. When the document went to the printer put it in the press wrong. And they printed the building code, 160 feet. Panic, what to do? The engineering committee said, we don't know anything close enough anyway, leave it go. True story. So, the limitation of 160 feet for a reinforced concrete special wall in the building code today is based on a shadow study and a typo. That's why it's there, not based on math or science. So today, when we're designing these very tall buildings, 1,000 feet or more, in places like San Francisco or Los Angeles, reflecting on the why of R and the why of 160 gives us two things. One is it gives us confidence to go a different way. We shouldn't be beholden to these rules that don't have any relevance to what we're trying to do anyways. And two is, today we have tools that we didn't have when this was all conceived in the 40s and 50s. We have the ability to model non-linearly the responsive structures. We have the ability to assess and test buildings with time histories and ground motions to really understand how our buildings perform. And so this is part of this journey of why that I've been on. When you start to peel back and you look at these classic engineering examples of why is it that way, and when you understand why, now you have some confidence in a platform that we at least pushes you to move on. I'm going to give you an example or two of some why questions I'm currently pondering. Those are two that were 20 years ago in my career. The next two I'm going to share with you are things that are in my head right now. And I don't know the answer. We're trying to figure out the why and the what we're going to do about it. So one of them relates to seismic engineering and wind engineering. So in seismic engineering, the philosophy behind seismic engineering of buildings is that under a modest earthquake, we don't want to have any damage. Under a moderate earthquake, we'll accept some amount of damage, and we can define that moderate earthquake as one that happens perhaps every 500 years. And then under the big one, and nationally, the big one is defined as an earthquake that happens one time every 2,500 years. That the building can be on the verge of collapse. It can be in a state that's unrepairable. We'll accept that. And in fact, what the building code has as an underpinning is under the 2,500-year earthquake event, it's expected that 10% of the building stock will indeed collapse. That is the basis of the building code. Not arguing that, that's what it is. In wind design today, when we design tall structures of note, the building code framework says Under a small wind event, we don't want any damage. Under a moderate wind event, the code gives no guidance. And under a maximum wind event, defined in the United States at least, as an event that happens one time every 2,000 years. If you want to be totally accurate about it, it's one time every 1,700 years. Long story why 1,700, that's another why lecture. This why lecture, except it's 1,700 years. That's the basis of the building code. And under that 1,700 year recurrence interval wind event, thou shalt remain elastic. No damage. And this is the way for 32 years of my career I've been designing buildings. Just accepting that, not asking why. Seems totally incongruent to me, right? In earthquake, 2,500 years, we're willing to get to the verge of collapse. Don't want it to collapse, we're trying to prevent that, but that's our design goal. But under a wind event of a similar recurrence interval, we must remain elastic. Wow, we are grossly over-designed for wind. What if we allow some modest amount of nonlinear behavior in a wind event and take some air out of the balloon, so to speak? Let the building respond to that and absorb some of that wind energy. Can't we design more efficient, more economical, more resilient buildings if we do it that way, rather than kind of blindly applying these elastic forces at some inflated value and design away? This is our practice today. This is one of the questions of why, in my mind, we're wrestling with today is why do we do it that way and how might we do it differently? So we're delving deeply into the realm of nonlinear wind design. And we've got a whole team of people around the country working on that. So there's one why. Another why, this one's fascinating to me as well. It's in the area of fire protection and fire design of structures. Today, required by the building code for a steel structure here, you can see we need to provide, in most cases, some type of fire protection for the structure. In this picture, you see a spray-on fire coating and a sprinkler system. Why? Simple answer. Oh, redundancy. Oh, yeah, of course. Why? I called up the National Fire Protection Agency, one of my good friends, Robert Solomon, is the chief engineer there, and I asked them that question. Why do we require spray-on fire protection or some means of protecting the structure and, in addition, a fire suppression system charged with putting out the fire? If the fire suppression system works, why do you need the other one? Redundancy, of course. I said, well, okay, I accept that. However, can you give me the basis? Can you give me the committee meeting notes? Can you give me the philosophy behind why that is that way? That these are the two things that equate to redundancy. What if, for example, instead of spraying all my steel beams, I want to create redundancy. I'll put in two sprinkler systems, completely independent and redundant with each other. One dry, one wet. I don't care, you tell me redundant. I've achieved redundancy, but I have enough code that tells me I'm going to do this other thing. What's the basis? Interestingly, the National Fire Protection Association, National Fire Protection Association, they can't tell me the answer. They don't know. It's their own rule. I asked them, if you look back to the 20s or the teens or wherever in your history, wow, we're going to have to dig into that. No one on the current staff for the National Fire Protection Agency can tell me the answer to that question. We're working on it. This is a question of why. Well, why am I even asking this question? Because in my day job, the architects I work with would love to expose that steel structure and have the people inside the building see the structure for what it is and not coated with all this spray on. That tends to flake and dust and create a mess. It just seemed maybe go away. Well, there's a way to do that now, right? We can paint it with a special paint. But the question is there another solution to this other than simply applying things to the steel? Don't know, we're working on it. Wow. All right, wow. Let's move on to the next and second question. So if you can answer the question why something is the way it is, now you have some confidence. You have a platform off which to build, and you may even start to see a way forward. The next question kind of goes something like this.
He's our broker. He helps look after all our money. Of course.
How much?
I don't know exactly.
What if you're not happy? Does he have to pay you back?
Nope.
Why not?
It doesn't work that way.
Why not?
Are you asking enough questions about the way your wealth is managed? Wealth management at Charles Schwab.
So the second question is not, do I invest with Charles Schwab? The second question to be asked and answered is, why not? There, kind of the innocence of a young child, asking very innocent, somewhat naive questions. Why not? Or, if you're being bold and daring, why not? Or if you're interested intellectually, why not? Why not challenge what's done normally and do it differently? Why not? So this is where I connect research. Ha! Mark. He asked me to connect this to research. And research for what I do in my day job, designing structural systems for tall buildings, is that connection to why not. It's when we've done something for the same way for a long time, and it's not quite working the way we want it to work. We ask, why not? Why not do it differently? Why not try something else? So here's some examples of why not. Simple example, and one of the first that I was involved in with the Pankow Foundation 10 years ago or so, is in seismic country, we design these shear walls heavily reinforced, and then we connect them together with these diagonal steel cages to deal with the shear force in that coupling beam. Very heavily reinforced. The contractors complained there's these little micro cages that were required by the building code. Very, very difficult to put together, very time consuming. Cost a lot of time on the job site to try and stuff all this stuff together. So the question, why not? Why not do it differently? How might we do it differently? Well, the idea was simple. Let's get rid of those little micro cages. Those are the things that are causing the problems and giving us alignment problems with the rebar. And let's just take the beam and simply enclose the beam with enough stirrups, enough ties to confine the beam and let the diagonal bars float free inside it. So it's easier for the contractor to place it, more quick for the contractor to place. This was the why not. Why not this? So what did we do? The Pankow Foundation graciously funded a research project at UCLA. We worked with Professor John Wallace, and we built a whole bunch of beams, and we broke them, and we showed that it worked great, and within 6 months' time, we changed the building code. And there's a new provision in the building code that allows this type of construction as an alternate. We didn't take the old thing out, we left the old thing alone. We added this as an alternate, and today, most of these beams get constructed and detailed like this because the contractors like it because they can do it faster. All right, that's a simple example, maybe a little pedestrian, a little mundane. Let's take on another interesting question. So a lot of these tall buildings that we design, there's concrete walls in them, many times around the core where the elevators are. And many times the floor slabs for these buildings are post-tension concrete. And the way in which contractors like to go about building these buildings, many times will advance the core of the building ahead of the construction of the floor slab. Calls into question, how do you connect those two? If the core is already built in advance, 10 floors above where the floors are going in, how would you connect those? Because the traditional connection was to take, in this case, in the detail, this PT anchor, there's a PT tendon here, and a PT anchor. That PT anchor would be situated back here in the wall, and so the anchor is situated in the wall, and that's okay if you're building the building floor by floor, build the wall, build the slab, build the wall, build the slab. It becomes very inconvenient if you want the wall to go ahead. How do you make that connection? And the building code didn't have any guidance for us. So the question is, why not? Why not connect this simply with rebar and leave the PT anchor be outside of the wall? And where outside of the wall might it be? So once again, research. Why not? Into the lab at Berkeley, built a full-scale test specimen where what we've got here is there's a one-story high concrete wall, a 30-foot concrete slab span with an 8-foot cantilever, a column. All of these little square things are dead load on the slab. put the rebar in, put the PP in, and then rock the thing back and forth, see if we could break it. Ultimately, we broke it. That's what we like to do in the lab. We like things when they make big noises and the whole building shakes. It's fun. Gives us the point where we don't really want to go. But what we did with this is we figured out detailing that allowed us to get the kind of behavior that we wanted, so that we ended up ultimately publishing a paper in the PTI journal that now has become the basis of practice throughout the United States for tall buildings. It's all based in that question of why not? Why are we doing it this way? Why not do it that way? All right. Another example. We design tall buildings all around the world. This particular building is in Hong Kong. It's a very, very tall, very, very skinny building in a high typhoon-prone region. We've been hearing about all the hurricanes in Puerto Rico and South Florida and whatnot. Similar situation in Hong Kong, just typhoons. So if you're building a building this tall, not only are you worried about strength, but this was a condominium, so we're worried about how the people might feel inside of it. Will they be comfortable when the big wind blows? And we're pondering this question, trying to figure out what to do about it. And during the design process, we were informed by the Hong Kong building officials that we must include in our building this huge water tank for fire water storage, because they, in Hong Kong, didn't want to rely on their city infrastructure to supply water to the building, to charge the fire sprinkler system. They wanted it to be more of a passive system charged by gravity. So they wanted a big water tank in the building, preferably on the roof. Okay, that's what you need, that's what you want. We have another problem. We're trying to design a building for wind. Why not? Why not use the water tank in some creative way to dampen the motion of the building? And some of you have seen me speak before. You've seen me talk about this before. Today I brought something new for you, a demonstration of sorts. And so the demonstration goes like this. I have two little models of a very simple single degree of freedom system. If I hold the base here and I push on this one, it vibrates back and forth, right? That there's some natural frequency to this building. There's some mass on the top. So I've got my two buildings. And in one of these buildings, I'm going to put a water tank. I'm going to put the water tank on the roof, like the Hong Kong building. When we first did this, we did this with scotch, but I got scolded for that, so now we do it with water. And I don't know if you'll all be able to see this. I hope you will. I'll do it a couple times. When I push on the same two buildings, with the same force, what you see is the building with the water in it quiets down very quickly, and the other building is still vibrating in the wind. Today we call this, when we came up with it, we called it a slosh damper because we were doing it with scotch. Today we call it a tuned liquid mass damper, or a slosh damper. And how it works here is a very simple diagram, right? Engineers in the room. There's an unbalanced hydrostatic force. More water pressure here, less water pressure there. There's an unbalanced force in the building that way. And if you can tune the waves in the tank to counteract the motion of the building, it quiets the building down. And so that's what we did. I'll show you again. It works lovely. And this in Hong Kong we built maybe 10 or 15 years ago. We've since built probably 10 or 12 more buildings with this why not scenario included. Another example, when we talked a lot so far in this presentation about concrete shear walls. Okay. Why not make them out of steel? Why, who says we got to make a shear wall out of concrete? Why not make them out of steel like that? Oh, how does that work? How does that behave? Okay. Why not? Into the lab we go. This time in Berkeley again. We build very large test specimens, this time actually funded by the federal government. For a project that we ultimately built in Seattle. But the notion was we didn't want in that building, for a variety of reasons, big concrete shear walls. We wanted nice thin steel plates for the floor of the building. So the research connected us to the why not. We were able to use the research results to inform our design to do something that's other than a concrete shear wall. Why not make it out of steel? A couple more examples on the why not category. Today, all the rage in the United States seems to be heavy timber construction. And in particular, high-rise buildings made of heavy timber. This is a building we recently completed in Minneapolis. It's not that tall, it's 8 stories. But it's made of heavy timber, and it's one of the first in the United States to use that technology, I guess tongue-in-cheek, right? The building method we're using here is how they built warehouses in the 1850s. Not really new. But anyway, we built it. It's all the rage. The architects love it, the brokers love it, the tenants love it. It feels good, it looks good. It's just this hip environment to be in, this wood structure. What we discovered in designing this building, though, was we're really limited on how far we could span, how deep the beams needed to be to get those spans, and the limitation was with the mechanical properties of the wood. In particular, the modulus of elasticity of the wood, because these designs tend to be deflection controlled, so if we had a higher modulus, we could make a better building. Why not? This is a question we're asking right now. Why not? Why not grow a forest with trees that are intentionally grown to build buildings with that have a higher modulus? Why not? They already grow entire forests of trees to make toilet paper. It's true. You need toilet paper. It's a commodity. They grow a lot of trees. They grow very fast, very soft to get the turnover. We want the opposite in buildings. We want wood that's hard. We want wood that's stiff. It takes a long time to grow that tree. Maybe. So we turned a few years ago to some of our friends in the forestry industry to talk about genetically engineering trees to grow buildings. Why not? They can do it. In fact, the geneticist that we were with said, of course I can do that. I know exactly the formula. We'll go do it tomorrow. The mills, though, said, no. That will take too long to grow. Before we have that tree, we'll all be dead. And to make matters worse, I suppose, the mills make their money on volume. It's a volume commodity business. It's not a specialty products business. So the more they can sell and the faster they can sell it, because they're making such a small margin on the wood, they don't want to grow this special, hard, engineered stuff that we want. They want to grow toilet paper. So at the moment, this idea is swaying down. The other argument that was offered to us is that the environmentalists would never let us grow that forest for fear of changing the world's environment. They're changing the way the squirrels fester or fuss around for their nuts and the way the deers roam around in the forest. And maybe there's a point to that, right? But I'd argue conversely, everything we eat has been genetically engineered. And if you think otherwise, you're fooling yourself, because it has. The seeds that grow the natural corn have been tinkered with. So why not tinker with a tree and make a better building? That idea for the moment is kind of on the holding pattern. All right, the last example I'm going to give you is one that's in the works right now. Today, in fact. So the premise is this. We've built for the last 20 years of my career many, many buildings all around the world, office buildings, where there's a reinforced concrete core, in this case, reinforced concrete core, jump formed way ahead, and steel floor framing that form the plates for the office occupants. This happens to be the headquarters for Amazon in Seattle. And it's indicative of many, many buildings all around the country. New York, Chicago, LA, Seattle, you name it across the country. This is how many, many buildings get built, office buildings. Okay? One of the things we learned is that the schedule of construction is totally driven by the ability of the contractor to form and advance the core. They can build the steel much more quickly. They can erect the steel almost twice as fast as the core. That's why in this case you see this big gap between the concrete, top of the concrete and the top of the steel. Because the way the contractor prosecutes the work is he wants the steel and the concrete to finish at the same time. And if the steel goes twice as fast as the concrete, he needs to be so far ahead to make that happen. So the schedule is fundamentally driven by the concrete core construction. Why not change that? Why not? So, we are. So what we're doing now is we're in the lab with Professor Barman, and we're working on a scheme where we take, in this case, you'll see side-by-side comparison of a traditional approach on the left here is a traditional concrete core, how we would normally prosecute building this building, and on the right is this new idea we have where the core, instead of cast-in-place concrete, is 2 steel plates interconnected by rods, empty, but erected with the steel frame in the same sequence as the steel frame. So the speed now is all about the steel erection. And then we come back later and infill those 2 steel plates in between with concrete to give the building the stiffness it wants. It doesn't need any reinforcing steel because the steel plates are the reinforcing steel. And the whole premise of this system is grown out of actually research that Professor Varma and Michelle Brunel at SUNY Buffalo have been working on for a number of years. We're taking their work and extending it into high-rise construction. This building will be another building for Amazon. I guess I wasn't supposed to say that. Anyway, there'll be a tenant in this building. And it's just starting construction now. The demolition was underway as I left Seattle. The building is 950 feet tall, so it will be the second tallest building in Seattle. It's mostly office with some residential on top. But you can see in this video already the disparity in terms of where is the building on the right versus where is the building on the left. When this video kind of completes itself, you're going to see at the end of the day, we're predicting between the new way and the way we used to do it, about 120 working days difference. Not calendar days, 120 working days. It's like 5 months. And if you're a commercial office building developer and you say, I'm going to save you 5 months, that's tens of millions of dollars because of the interest carry on his loan and because he could rent the building 5 months earlier so the cash starts flowing 5 months earlier. It's literally tens of millions of dollars to be had by the developer using this new approach to building the building. All right, so the building on the right is now done. You can't read the number, I'll read it for you. 377 working days from when we started the foundation to when we topped it out. And the building on the left is trying to catch up. This time, nearly done. Punchline here is the building on the right, or the building on the left is 490 working days, so 120 days difference. So time will be will tell the tale here, right? We're building the building. It's physically under construction. We're trying to take the design that we made for that building and improve it. We know our design is conservative, and this is what we're working on in a lab here in the Bowen lab to investigate ways to improve that design to make it go even better and make it also applicable in environments not just seismic, but wind. So the Charles Pankow Foundation, the MKA Foundation, our own company, and Purdue University, we're all working together along with AISC to fund a project here at Purdue. It started actually 6 or 7 years ago, where we worked with Professor Krager and Professor Bowman on this 5-story tall specimen that we had in the Bowen lab, where it was a T-shaped section of this construction. And we filled it full of concrete and we pushed on it until we broke it. That gave us a lot of confidence to go ahead and proceed with our design, which this has been the basis of how we've made that design. But as we've gone through the design, we've come up with a number of other questions. How can we improve it? How can we make it better? So then we engaged Professor Varma and his team to try and advance it and make it better. So if you go out to the Bowen lab today, you'll see there's actually a test specimen, one of these, in the test rig in the lab that they're testing today. And you'll be able to see some of the testing live, in progress going today. It's first one of 6, and hopefully from this, we have actually a multi-year test program where this is kind of the first series of tests. After we get the results of these tests, we're going to ensue into a whole series of other tests to help kind of advance and perfect this. So again, why not fuel this idea? All right, so I'm nearly done. 54, almost on this time. So, I was joking with Professor Bowman earlier. I had Professor Bowman for advanced steel design my senior year of college at Purdue. And I remember very clearly at the conclusion of our class and at the end of the final exam, and we're all sweating from our toils, and after thinking about the why and the why not, and oh my God, and it's all sweat, Professor Bowman says, why not? And we all went for beers and had a good laugh. Why not? let's go have a beer and have a good laugh. Thank you very much.